All right, so we're doing the weird clown problem, number 54. I give this one every year just because it's disturbing. All right, so let's think about conceptually what's happening. We know what the clown is standing on the ground. We'll make it AstroTurf. All right, and there's some coefficient of friction we know between his feet and the ground, so we know it's frictiony. All right, so the harder he pulls on the rope, the harder it's going to pull on his feet, but also it's going to do something else significant. What is going to happen when the clown pulls on the rope? Well, he does increase the tension, and that's what's going to pull on his legs, right? But if he's pulling on the rope, the rope is pulling on him, okay? So if the rope is pulling on him, what significant thing is happening that affects how much force it's going to take to pull him this way? I'll give you a hint. Okay, what about friction? Is it going to change the character of the surfaces? So it's not going to change mu, is it? How might it change friction then? If it's not changing it by... It decreases the normal force. Excellent. Yes. When he pulls on the rope, it decreases the normal force. So not only does he pull on his legs harder, there's less friction to keep his feet from moving with respect to the ground. Does that make sense? All right. It's a little bit weird. So now, drawing a free body diagram for the clown. What? A free body diagram? Here's what we got acting on the clown. Let's think about this. What's going on? We got what? Well, we got gravity. All right, we'll start with gravity. We got normal force. What? We got normal force, which is what? Normal force exerted by what? The ground. Or is it one or the other, or is it both? Yes, it's both. All right, we got normal force and we got tension. Okay? So now what else do we have acting on the clown? Tension. What about this tension and that tension? They're the same. Yes. Okay, we take the tension to be the same all the way through a rope. So by however much he's decreasing his normal force by pulling up, he's also increasing the sideways force. So we want to know at what point how much tension he has to exert in order to yank his feet out from under him. Okay? So I would imagine that we are given mu. What is mu? 0.53. Okay? We're probably also given the mass of the clown. Or does it matter? 899? Oh, his weight is 899 newtons. So weight is equal to 899 newtons. So that's mg all in one package, right? 890 O? All right, 890 O. Newtons. All right, so that's weight, like I said, all wrapped up in one. Okay? So now, we're trying to solve for what? We want the tension to be equal to what? Let's think about it. We're trying to solve for the point or that tension where what happens? All right, so we want tension to be equal to friction. Does that make sense? All right, we want because we're solving for the threshold. Well, you could say we want it to be greater than the friction. Yes, we do, but we're going to solve for when it's equal. Okay, so the tension is equal to the frictional force. What kind of friction is it, by the way? It's static. Could you tell because I hadn't written it yet? Ooh, it's all in pieces. All right. So solve for this. All right. So that looks like a pretty simple expression, but what's going to happen? It's going to blow up into a lot of stuff because we're going to have to evaluate a lot of different things in order to solve for tension and static friction. Okay? Everybody okay with that so far? We're solving for tension. All right. So static friction is going to be equal to what? mu times normal force. And what is normal force going to be equal to? Now we're going to have to go to the free body diagram, aren't we? Okay? Normal force up here, what do we know about what's going on in the y direction? Is he accelerating in the y direction? No, he's not accelerating in the y direction, right? He's decreasing the normal force, but he's not going up or down, right? He's not accelerating upward or downward. The net force in the y direction is equal to 0, right? That's why we're decreasing the normal force when we increase the tension, right? Because it's all got to equal mg. So net force in the y direction is equal to T plus N minus mg. Tension and normal force acting upward, negative mg. It's acting downward. So tension with the normal force is going to be equal to, here, let's just set it all equal to 0 and we'll do it step by step. T plus N is equal to mg. You guys okay with that? All right. So normal force is going to be equal to mg minus tension. Does that make sense? So now let's take a look at what we got. This expression right here now becomes tension is equal to mu times mg minus tension. And now it's just a matter of algebra, isn't it? Getting to here was the kind of weird part, because you have to take tension into account twice. So now we have 2t is equal to mu mg. So T is equal to mu mg over 2. All right, so mu is 0.5 something. What was it? 5.3? 5.3 times mg, 890 newtons. That's his weight, divided by 2. All right, so T is equal to half of 890 is 445. And then 0.53 times that is about half. 445, 220, I don't know, about 240 newtons? 235.85, so 236 newtons. Looks like it should be the answer. And what is this, an even or an odd one? This is an even one, so we'll check the purple book to make sure that we did that one right. Okay? Any questions? Good one. All right, cool. All right, so Sam asked the question, why did we not distribute the mu right here? And I said, because I was wrong. All right, so we got to go back and fix that. All right, so it's not 236 newtons, even though we got that as the answer. So let's fix it. All right, good thinking, Sam. All right, so now we have to distribute that. Mu mg minus mu t. So now we get t plus mu t is equal to mu mg. Who's got the purple book, by the way? Is it in the back? Okay. Can you guys start looking this up? All right, so then we get t times a quantity 1 plus mu is equal to mu mg. So now we're going to need to use calculators. So t is equal to mu mg over 1 plus mu, and we'll just plug our numbers in now. T is equal to, mu was 0.53 times mg, 890 newtons, divided by 1.53, right? And somebody help with the calculator on that? 308.3. 308 is close enough. I'm going to take that to be correct, and we'll check one more time to see if I messed something else up. And the purple book says 310, but that's sig figs, so we'll take that to be right. And I only embarrassed myself once.